Thank you, Peter, for the introduction. Yes, so today is indeed an introduction concerning the decoupling of higher dimensional zero curvature hypersurfaces. Why higher dimensional? Well, in 3 dimensions, that case has been wrapped up. So just the 4+ dimensional case remained. All right, this talk will proceed by way of an introduction first, rather broad introduction to just go over some of the basic tenets of decoupling, i.e. the definition. And then we'll move into the second section, which will be the main result. And then we'll look at the proof in 3 dimensions as a warm-up to considerations that have to be indulged for the 4+ dimensional case. Let's start with some notation that will recur throughout the talk. We have the usual abbreviation for the complex valued exponential function. There will be a distinction between points in frequency space and time space. In particular, the hypersurfaces that we will be considering will lie in frequency space. All functions up here will be Schwartz so that we have Fourier inversion. This is a notation that will also be used for the Fourier projection. You just project on the frequency side to some set S and then transform back. Now phi will also be central here. It is the moment curve and in dimensions. Now, because of the fact that we're dealing with hypersurfaces and a certain like very gentle level of surgery will be needed on these hypersurfaces, we need to define a cap. So given some hypersurface M, that is an n-dimensional Euclidean space, we have the normal vector n, some arbitrary delta that we want to think of as being pretty small, but yet positive. And then a subset of M is called a cap relative to delta. If it is contained in this translation of the tangent plane along the normal direction, a translation that extends, that gives at most delta square thickness to this created slab. Now, this is not a very new definition. In work done by Josevich, Sawyer, and Seeger, they introduced these caps as a means of obtaining their solution to the Bourgain-Demeter problem for convex hypersurfaces of finite line type. They are able to prove that theorem up to the Stein-Thomas index. And these caps are used as a means of obtaining estimates on the Fourier decay of measures supported on these hypersurfaces, which in turn that was obtained by work of Brunner, Nagel, and Wenger. So we are keeping with tradition to some extent in using these caps. Any questions? Yes.
Sorry, my basic question. Why any S wouldn't suffice with taking just psi and 0?
Sorry, one more time, I didn't catch the first part.
Do you think of psi as originating at the origin or at the point?
Psi or S, or psi, right, at the point. Well, okay, you can pick some point in S, let's say, and call it the origin if you like. This will be the local coordinate description of manifolds. But otherwise, we're just taking some hypersurface, any hypersurface. You can think of it as a graph of some function if you want. That's perfectly fine by differential geometry. And then if you were to do that though, the normal vector is what we're thinking of as the nth standard basis vector. I'm not sure if this is your question.
I just don't understand why any point Q wouldn't satisfy that condition with psi and V being 0.
Right. Any point Q. Okay, so I think okay, one more time, you're saying if any C, for any Q, allow Q to be arbitrary and C to be 0.
I think a picture.
Yeah, draw a picture with
a picture on the blackboard. I think it would clarify. I mean, if you do it on a sphere, it's like a spherical cap, right?
Right.
Oh, sorry, Q is fixed before
Right.
the bracket. Okay,
Right.
okay.
Yeah, I was gonna say that, but then I wasn't sure if there was something else there. Okay.
Yeah, I think it's clear.
Okay.
All right.
Yeah, so that's how it looks like.
Yeah, for some fixed Q. Okay. Were there any other questions? All right, given some wave F, we may seek information about F by studying composite waves whose frequencies lie within small regions. So we have a function F that is Fourier supported and some set S, and that same set S is partitioned in the smaller subsets Si. And corresponding to that is the decomposition of the Fourier projection of F onto S in terms of the sum of Fourier projections along the Si. Now in the realm of L2, this is standard that there's square root cancellation that applies concerning the relation of these Fourier projections to the SI. There are L2 norms and the L2 norm of the original Fourier projection. And decoupling can be seen as sort of motivated by this square root cancellation. You'd like to generalize it to arbitrary p-values. Right, so initially, there is this proposition obtained by way of the Plancherel identity combined with interpolation. So we have that for under fairly general conditions concerning those SI, such as just being balls or cubes with pairwise disjoint doubles, so that we can interpolate. There is this inequality that holds for all P and R larger than or equal to 2. And it is a little LR sum of LP norms of the Fourier projections. Let's pay attention to the exponent here. It's 1 minus 1 over P minus 1 over R. And decoupling is meant to improve that same exponent to something smaller. Now this inequality too is called trivial decoupling in the decoupling literature. And it's actually sharp when the SIs are equidistant, translates of some fixed set S along a fixed direction. To rephrase that a little differently, this proposition is telling us that we want to avoid lines and we're looking to L2 decouple. Excuse me, sorry. Meant to hit the pointer and hit the wrong button. Right. I may have to move to the next slide in order to say more. So this definition of LR-LP decoupling in particular looks the same as before, but the exponent has been reduced to 1/2 minus 1 over R. And now this is what I was trying to get to. When R is 2, you don't have any power of n, at least unless you've read to this part, which says that we allow at most some epsilon dependence in the exponent for n. But in particular, modulo that loss, there is no positive power of n, whereas trivial decoupling is telling us that there must be, right? Well, you would have here 1/2 minus 1 over P for L2 decoupling, or not L2 decoupling, if P is equal to, if R is equal to 2. That exponent would be 1/2 minus 1 over P, which in particular is positive when P is larger than 2. And so that's why when we're seeking to L2 decouple, we have to avoid lines because this proposition is telling us that we will always have very bad loss in the constant when we try to decouple some neighborhood of a line. So my goal here is to motivate why we have to use hypersurfaces when seeking decoupling results. And now the relevant values of R during this talk will just be 2. Actually, this was a typo, just 2. And P will, the range for P will be specified given the context that we're in. Okay, any questions before I continue?
So this dec PS is the best constant,
Right.
by definition, best constant for the decoupling for S and P.
Yes, and key point.
Give estimates for that.
Right. That's our goal.
And
Is to
you're very happy to give up an epsilon.
yes, for any positive epsilon. Okay. Now the zero curvature and dimensional hypersurfaces can be introduced by way of this n-1 dimensional moment surface, which is obtained by way of the moment curve. So we take the moment curve and then we look at the first n-2 derivatives of the moment curve. And then for each such derivative, we introduce parameters Si that allow us to extend along the direction prescribed by that derivative vector. And adding all this together, adding all of this up, it generates a hypersurface. Just to give you an idea of what this looks formulaically, here's the computation in 5 dimensions. And we want to decouple thin neighborhoods of this hypersurface in arbitrary n dimensions.
Those EJs are the derivative of the moment curve causation.
Right. Yes, to reiterate, phi is the moment curve, t squared through tn. And so each one of these is the first derivative and the second all the way up to the n-2 derivative.
So it's the moment curve, and then the S's are just the vector 1 S1 up to Sn, and that's the inner product. I mean, where did the moment curve come from? I know why it's so useful, but why did you introduce a moment curve at this point? You're trying to do decoupling for hypersurfaces,
Right.
And you're going to try to deal with a general hypersurface with some curvature conditions.
We're going to deal with a small class of hypersurfaces that are meant as sort of a warm-up for future research into a more general setting.
Okay, all right, let me wait. All right, so you introduce this hypersurface.
Right. So, in particular, I just mentioned before that lines are bad, but now we have a hypersurface that is very explicitly spanned by lines in n-2 directions. You only have one direction, which is essentially the direction of the curve itself, the moment curve. Right, but everything else looks rather linear, and this should be problematic if we want to find LT decoupling, right? And so what this talk will be geared towards is showing that a cylindrical approach to decoupling of zero curvature hypersurfaces can get us quite far.
Is there any like nice picture or cartoon of what this looks like when n equals 3?
Yes, there is actually. We can skip ahead to that slide. And so while we're here, might as well just kind of look at this purely from an aesthetic perspective. It sort of looks maybe like it could be a parabolic cylinder, but one that is constantly being changed, right? Another way of saying this maybe is that it looks almost like a cone. And it's been known that cones locally look like parabolic cylinders.
What's a parabolic cylinder?
Oh, sure. It's the parabola in a plane, let's say, if we're in 3 dimensions, like an honest plane. And then you just take an orthogonal vector to the plane and then extend, right? So before we get to this slide, I wanted to, maybe I need to explain why using cylinders is a good idea for decoupling. So there is this well-known proposition. So we have some inequality. We can just think of it as being decoupling inequality. That will be prescribed in C to B of a very exact form. But this fact is true regardless of what we know about C or don't know.
So you're assuming decoupling for S, and you're gonna now.
Right. Oh, it's the exact same constant. This is the main point. And the proof of this is Bourgain-Demeter combined with Minkowski's integral inequality. And this was actually a rather core element in the original proof of L2 decoupling done by Bourgain-Demeter. Their proof was an inductive one, induction on the dimension. And so there, it becomes pretty evident that you would want some form of this in order to take a result that you have, a decoupling result that you have, and say R3, and then use that for a result in R4, and then continue iteratively. Any questions? Okay. Right. Okay, so we've talked about one essential element of, well, one convention rather that occurs in decoupling proofs. There's another one. So if you are familiar with the Bourgain-Demeter result for parabolic decoupling, or if you've read other decoupling papers, some form of parabolic rescaling or analogues of that are needed when you have an iterative decoupling scheme that you are wanting to execute. This lemma should be viewed as a reformulation of parabolic rescaling. Maybe not, that's too strong of a statement, but what we're trying to say is that it does half of what parabolic rescaling accomplishes for the paraboloid. So this lemma allows us to translate in the t direction. Let's examine the content. So we have some map A, some affine linear map. Interestingly enough, it actually looks pretty similar to the Taylor series formula. But remember that these Vj's are vectors. And these are the vectors that form the columns of the matrix for A. And you're multiplying each such vector by the jth component of C. You do need the j factorial underneath. And TO is fixed between -1 and 1. Now, given some function FTO, which should be thought of as just combining on the frequency, composing on the frequency side with A, these statements are true. The first statement is telling us that A preserves the moment surface. It just, when you apply A, it merely moves whatever point you have in the moment surface to the point with the same S values, but now with a translation by TO applied to the first coordinate. And then the second statement tells us that when we apply A to functions F, we are not changing the LP norm. So this map A both preserves the moment surface and it preserves LP norms of arbitrary functions. Now this fact is just change of variables combined with an observation that this matrix here is upper triangular, rather lower triangular, with ones along the diagonal. Any questions? Okay, we're just putting together our tool set to warm up for the proof.
Why is this weaker than parabolic rescaling?
Right, because parabolic rescaling in particular involves rescaling, and we're not rescaling the manifold. We're not enlarging the T interval, for example. We're just moving it around. Whereas parabolic rescaling not only enlarges size of subsets of the paraboloid, But it also in particular moves them back to the origin.
So we don't have the rescaling part.
Right, we don't have the rescale. Right, that shows up somewhere else.
Okay.
Any other questions? Right. Okay, now why is this useful for decoupling, even iterative decoupling? Well, let's say that in the course of our proof, we have some function f that is Fourier supported and the neighborhood of some subset delta, just having this general form here. Then the Fourier support of FTO is somewhere special. It's in this new subset, which in particular now has the t coordinate bounded by the length of this former interval. Here, t might be in a small region because t1 minus t1 might be pretty small, but it would still be forced to be big due to the lower bound of TO. TO could be pretty large. In fact, it would have to be because we're wanting to allow, we're taking a hypersurface that has t going from -1 to 1. Right. But if we can instead make t1 minus TO now the upper bound and the lower bound 0, then we're good. This will be helpful for having self-improving decoupling error in the course of an iterative scheme. Okay, so all this to lead up to the main result that is obtained. You have this delta neighborhood, which we just take, say, the nth standard basis vector, which is in particular the actual binormal vector of the moment curve when t is 0. And then we have this new result for all p between 2 and 6. This is an honest L2 decoupling that holds. Now, concerning these deltas, they are the caps that we saw before, which we know is good enough for most purposes, such as in the Josevich, Soya-Seeger endeavor, although we're not dealing with convex hypersurfaces here. But the main point that I want to say here is that these caps are in a way not quite optimal because they still may have curvature. They're flat concerning, I don't know what happened to that word, but concerning the normal direction, what I was going to draw to you at the beginning of this talk. They're flat concerning the normal direction, but in terms of what happens in the tangent space, what happens, yes, sort of along the hypersurface, these caps appear to still be curved. So now this actually is a moot point when we're in 4 dimensions. We do have the fully almost rectangular subsets that we would want for this theorem. It's just that in 5 dimensions, the caps that are obtained are not quite flat. Yes.
Is P at most thickness sharp decoupling exponent?
Yes, it is. And that might be surprising too. Thank you for mentioning that. This is true for all dimensions n, which might seem unusual because, for example, the paraboloid has its decoupling range for P with an upper bound that depends on the dimension. But this is what the parabolic symmetrical decoupling approach provides. It shows that the decoupling theory of these moment surfaces essentially reduces to the decoupling theory of the parabola, which we know that to have a range for decoupling from 2 to 6. Now, at the same time, it does not appear that the parabolic symmetrical decoupling is sufficient to get us all the way down to the flattest possible caps. It's only good enough to give us caps that extend at most delta along the normal direction. So you would have some set, and the idea is that relative to this normal vector, the cap is going at most delta. Now, this theorem holds more generally for surfaces of this form, where you replace phi with the non-degenerate Cn-1 curve. And that follows by the Harmonic-Seeger induction on scales method. Any questions before we continue?
So first you had the moment curve.
Yes,
Now you've got these more general ones.
yes.
What are these surfaces? Do they have another description? I mean, you're proving, for these, you're proving sharp decoupling, I guess.
Yes.
And I'm just trying to understand how rich they are or what. Is that something you'll address? Or at least in low dimensions?
I mean, maybe somewhat unsatisfactorily, in the sense that, if you think about the classification of zero curvature hypersurfaces in R3, it's telling us that essentially a zero curvature hypersurface is comprised of a curve and then some set of lines.
Right, so close to this.
Right, so the same, using that same motivation, we would expect that zero curvature hypersurfaces and n dimensions would look like lower dimensional Euclidean submanifolds with lines or planes rather sort of associated to.
Okay, so in dimension 3, you said it's completely resolved. And in dimension 4, does this come close?
I don't think so, but it's also not known. There's no, to my knowledge, there's not a classification of zero curvature hypersurfaces.
So for us who are not familiar with all this, the first thing is, of course, I guess positively curved. Then that's one situation which is probably classical. Then there's the parabolic case. That's the main case. And now you're doing this where you're like zero curvature, kind of cone-like, flat pieces. In dimension 3, they're ruled surfaces, these?
Are they? Roads?
Yeah.
Yes.
Yeah. Just trying to see the picture, because it's, you're getting into the details, so I'm trying to see from the top what you, which.
What's the definition for M2K minus 1? Is it arbitrary smooth?
No problem. You can go back to it. So phi is the moment curve.
This particular moment surface, I see. And I see. Yeah.
But the theorem says that phi can be generalized to any non-degenerate Cn-1 curve.
So you generate a surface based on this curve.
From the moment curve.
And hopefully that's the first step.
Right, exactly. It seems reasonable that you could take, say, a two-dimensional surface and then extend along the derivative vectors of the parameterization for that surface. And then
That's the one
C2.
you showed in 3 dimensions. That's the one you just showed us.
Oh no, I'm purely speculating. This is,
Oh, okay.
yes, yet to be realized. But the idea is that zero curvature hypersurfaces and higher dimensions should at least maybe frequently should look like lower dimensional parameterizations involving the derivative vectors. Okay, right, so in 2014, the first optimal L2 decoupling theorem was provided by Bourgain-Demeter. And this was the starting point. Provides to us an actual decoupling engine, if you will. But we only need this theorem for the two-dimensional case, n equals 2. And in that case, you partition the parabola into subsets, or rather intervals in the horizontal axis, intervals of length of essentially delta to the 1/2. And then for each p between 2 and 6, n being equal to 2, we have an honest L2 LP decoupling inequality for all functions that are Fourier supported in the parabola. Now remember, according to symmetrical decoupling, we can extend this inequality to functions that are Fourier supported over the parabola across some R, some line. Okay, so when we do that, this corollary follows. You can apply symmetrical decoupling iteratively, of course. And so you have something that applies for however many components are involved. So in particular, we have a full n-1 component or n-2 components that are allowed to be completely arbitrary. And now the if component is being squared, and then the eta corresponds to some parameter that describes the width, the neighborhood width. So that's why we keep track of the size of eta here, so that this parabolic symmetrical neighborhood should be thought of as having thickness E. Okay, so when we do that, then we partition the CI axis corresponding to the C there. We can partition the CI axis into intervals of length e to the 1/2. And then this corresponding decomposition of the parabolic cylinder is provided. And for each of these thetas, they appear here in the sum that we're taking for an honest L2 LP decoupling inequality. And P is again between 2 and 6. Any questions? This is kind of our main thrust here. Corollary 2.4 is what gets applied over and over again. And the point of the proof is to determine how to apply it. Okay. Now, what should maybe raise some alarm is that we're dealing with two descriptions of our hypersurface, right? There was a parametric description that was given to you initially. That's where T's and S's showed up. But then the parabola follows the actual Euclidean coordinates, the C1 through Cn. And so there needs to be some bridge established between these two descriptions of our hypersurface that we have. Because corollary 2.4 applies to Euclidean coordinates, but initially our actual decoupling theorem is described in terms of the coordinates that are particular to the hypersurface itself, the T through S1 all the way up to Sn-2 variables. So this condition is that bridge. We consider the T derivative of Ci, the same Ci as from the previous slide. Ci composed with our parameterization X. And we want that derivative to be essentially 1, bounded from below. And when that holds, our previous corollary 2.4, seen here, it provides a lemma here where it's the same L2 decoupling inequality as before, but now we are thinking in terms of a cap, or not a cap rather, but a subset, need not be a cap. A subset of our hypersurface that is being partitioned into smaller subsets delta prime, where the T length of those subsets is e to the 1/2, corresponding to the partition of our
between 2 and 6 again. What's P?
P. Yes, P is well. Yes, between 2 and 6. Any other questions? Some drinking, we might as well have a mental break and look at the nice picture again. So we only talked a little bit about this picture actually. It's not only provided to you this portrayal of what the moment surface looks like in 3 dimensions. It's also portraying some of the caps in the decoupling partition. So notice that these caps, the sort of linear side, if you will, these are honest lines in the hypersurface. So those line segments get longer as you're moving away from the moment curve. This is the moment curve here, by the way. It's at the very end of our hypersurface. Now, while the long side, the length of these caps is getting larger as you move away from the moment surface, the width is actually getting smaller. And this corresponds to what's happening with the single non-vanishing principal curvature for its hypersurface. Any questions?
You're saying these caps are getting longer and skinnier.
Yes.
Does the area stay the same?
Does the area? No, it's not. A good question. I can tell you that the width is, okay, let me proceed this way. The length is some dyadic power, let's say 2 to the minus k. And that's going from delta to the 1/3, 1 over 3, because we're in 3 dimensions. And then it goes up to 1. So 2 to the minus k between delta to the 1/3 and 1. Okay, so this is 2 to the minus k, but then the width is 2 to the k delta, all raised to the 1/2 power. So yeah, there is not going to be the same. All right, so the 3-dimensional case was taken care of a few years ago, and it was done in a way that focused on the conical description of moment surfaces. But, and so that's why we have the formula here, which is, this in particular here is the formula or the graph of a cone that's been rotated onto its side. But cones, again, as we know from work by Bourgain-Demeter, what also shows up in the reverse square function estimate for the cone, proven by Rayshon, Larry Guth, and Han Wan. We know that cones can be approximated by parabolic cylinders, and so it would follow then that our 2-dimensional moment surface should also be approximable by parabolic cylinders. And let's see how we might obtain that. We start very simply. We just take the second component, square it, and examine the difference with the C3 component. And again, we're in 3 dimensions, so this is our last component. And this is what we find by direct computation. There's a t squared term, 3 minus 4s, and s. The s here is not relevant, but we do care about 3 minus 4s, and we'll see why. And the OT cubed is actually a really good error for iterative decoupling. In the same way that Bourgain-Demeter were able to find L2 decoupling for a more general class of hypersurfaces from the decoupling of a paraboloid. This is also, again, here y to t to the 3rd power is good error. We would like to see how we can make 3 minus 4s small relative to delta. And our tools for doing that is an intermediate decoupling combined with rescaling. So as before, we partition the 2-dimensional moment surface into annuli of this form. All that's happening is that the S is being restricted to be essentially some dyadic power. And then the inequality that follows here is just an application of the triangle inequality with floater. So using the most rudimentary tools that we have from graduate analysis. And it's fine, the loss that we incur in the constant, because log of 1 over delta, of course, has delta to the minus epsilon upper bounds for all positive epsilon. And this is pretty standard within the world of restriction theory, especially when dealing with degenerate hypersurfaces or the ones that have vanishing principal curvature. we want to apply some initial decomposition of the manifold that makes certain parameters essentially a dyadic power. Okay, now the equality of taking the C1 component and squaring that and examining the difference with the second component. This was actually done in the first paper, the first paper on moment surface decoupling. We apply that here again. And it provides to us from the parabolic cylindrical decoupling lemma 2.5, given to you before, this inequality, which is decoupling in L2, little L2, but for these Fourier projections, the same ones that show up here. And so we can combine these two inequalities to get an inequality for the original Fourier projection. Can merely insert each term here in the place of this with, of course, an intermediate inequality symbol. This is why decoupling is very good for iteration. And now each new cap in the script A case has a reduced T interval. So S is staying fixed now in this case, but T is being reduced to having interval length the size of the S variable. Okay, so again, our goal is to make 3 minus 4S small, and we're about halfway there now at this point with these smaller caps, delta 1. Okay, so then we need to further position these delta 1s, and we do that in a way that maybe seems really technical initially, because why are we partitioning the S interval, which we know in particular is the direction of lines, right? That's a bad way to decouple, it seems. But we can get by as long as we're doing a very sort of minuscule partitioning of the line segment. These subsets, their number is delta to the epsilon, delta to the minus epsilon, excuse me. Because again, all these intervals lie within 2 to the minus k up to 2 to the minus k plus 1. So you're dividing a 2 to the minus k interval into subintervals of length 2 to the minus k delta epsilon. So we have by the triangle inequality, excuse me, plus folder, this delta to the minus epsilon over 2 loss. And then terms fitting within an L2 of LP sum. And delta 2s have this reduced S interval. Okay, back to the question that someone asked before about parabolic rescaling and the answer given about rescaling not showing up. Previous lemma, the first lemma that we have, here we do rescale, and it's in this different way, where we are able to rescale these smaller subsets, delta 2. This is why we acquired them in the first place. We take the same A that shows up here, and we apply this particular rescaling of each component, and the image will be in the same moment surface, but now, and everything is nice about the T length. You do have to keep track of how the neighborhood length has changed from delta to some delta prime, but that's fine. You're not changing the overall context. You just need to keep track of what delta prime is for when we're at the end, when we arrive to the end of our strategy here. But this is what we wanted. We wanted the 3 minus 4S coefficient to be small. And indeed, the S parameter for these images is now within delta epsilon of 3 over 4. So we've achieved that. Right. And so what follows is that for the points in these rescale caps, this difference that we looked at before, in order to apply parabolical cylindrical decoupling, it has a very good coefficient for the t-squared term. So now when you iteratively decouple, you would first have to have the upper bound of this expression, which we can just say is delta to the epsilon. Is that clear? Okay. And if you take delta to the epsilon as the upper bound on this distance, then it's telling us that our delta prime cap lies within the delta epsilon neighborhood of a parabolic cylinder. And so then we obtain caps of length delta epsilon over 2. And okay, so there should be one more delta epsilon over 2. Right, and then now taking delta to the epsilon over 2 for those new caps that we obtained and putting it here for the t squared term. Our new upper bound on this expression would be delta to the 2 epsilon. Apply decoupling, you have to take the square root of that, and you get caps that have t length delta to the epsilon. Put delta to the epsilon in for the new caps. This upper bound becomes delta to the 3 epsilon. This should be delta to 3/2 epsilon. So my apologies that I rushed through this part when I put the slide together, but hopefully it's clear. I can rewrite the diagram if we need that. Basically reduce all of these by, or even just
Divide by 2.
divide by 2 and skip. Okay, so this type of iterative decoupling was first demonstrated by Bourgain-Demeter for conical decoupling, and they obtained the optimal decoupling theorem for cones in any dimensions. And furthermore, the roots of this idea, again, are from Harmonic and Ziegler and their work on maximal averages associated with curves. Any questions? Okay. Now, in higher dimensions, there's an additional degree of complexity because this t term arrives onto the same simply from the course of computing. It's coming from the fact that you now have an S2 because it's an additional dimension in 5 dimensions. There's an additional line that appears in our hypersurface, the one going along the S2. So in this second step of our procedure here, S2 would be the target T length, and then afterwards we may rescale as before. Proof theorem 2.3 in the case of 4 dimensions.
So maybe you can go back to theorem 2.3. I can't remember what you're proving anymore. So you're proving.
I think I may have meant theorem 2.2. Sorry, let me just go back to this slide. Yes, I meant theorem 2.2. And that is here.
So there's in any dimension for these surfaces, decoupling in P between 2 and 6.
Right.
Okay, and you had got up to dimension 4 and 5, you were explaining.
Right. Right. 4 was just taken care of, and now we're looking at 5 and higher. But already in 5, we have new difficulties. And so as we're wrapping up this talk, we just want to motivate how that new difficulty is managed. So, okay. Whereas before, for the 4-dimensional case, our proof was divided into basically 2 steps, corresponding to the fact that you have yes, this is redundant. We just want to be entirely clear. So this was the first step to consider. And the second step, sorry. Was then to consider this difference now. Actually, there is a third phase, but there's no, it's just a matter of like taking the fully baked cake out of the oven at that point. You're not doing anything here compared to what was involved in the first steps. But you do what you might anticipate. Consider this difference. And that pretty much applies for every dimension that we're going up for each case we have to consider. Right, so here, the second step, it's the same second step as written on this board. And our target length, which is also the same as the completion of the second step, is to reach caps that have T length S2, where S2 is, as before, fixed to be some dyadic power. Right, sorry, I keep switching back and forth, but I need to say one more thing. It is nice, even though this T is something new that we have not considered before, in 3 dimensions and 4, at least the coefficient here is exactly what we want to get to. This is good because what you can do is you can treat the upper bound here as being S2. And then applying the parabolic cylindrical decoupling lemma, the caps given from that lemma will be S2 to 1/2.
It's with S2 fixed.
Right, with S2 fixed, yes, S2 is fixed. Fixed dyadic power. Now you take S2 to 1/2 and you plug it back into T and consider the upper bound of this, which will be essentially S2 to the 3/2 power. Take 1/2 of that when applying parabolic cylindrical decoupling. It gives you S2 to the 3/4 power. But I want to write it in this way, which is just the same as 1/2 of 1/2 plus 1. So as we're trying to motivate, there is a nice pattern that is occurring here. So the geometric series with ratio 1/2. And that sum is 1, but you need infinite steps to get to 1. And so this is why we stop at 1 minus epsilon, which is good enough because you can apply a triangle inequality and floater to get all the way to S2 from that point. But you want to keep track of how many steps is occurring to get to S2 minus S2 to the 1 minus epsilon. And this is fine. It just needs to be a nice function of epsilon. Okay, I think that is it.
Questions?
Yes.
What are the sharp examples for these surfaces? Is it like a standard constructive interference example or something else?
Oh, sharp examples. Yes. Right. You take the characteristic function of the delta neighborhood of the hypersurface and plug it into the L2 decoupling inequality and compute what the constant would need to be.
It's kind of funny that the exponent doesn't change with the dimension.
Right.
And that's because you're projecting all the time. The method is to project to dimension 2, right?
Right. Yeah, but also too, it maybe seems less strange when you keep in mind things such as Greenleaf's work on restriction theory in relation to principal curvatures. But right, so the point is that within the world of restriction theory, which decoupling is, fitting in that nice circle of ideas, along with Bourgain-Demeter and other topics, principal curvature is what matters. And so it's because these hypersurfaces have all vanishing principal curvatures except for one that reduces everything, sharpness of the range, the proof strategy, if you will. It's all reduced to finding similarities to cylinders.
You have applications.
That's to be studied next. Yes, if you wait just a little while, there should be. Well, okay, so this hasn't been put on the archive yet, but I plan to do that this month. And then there's a paper that will be a follow-up to this, which I think should come shortly after, but maybe 2 months into next year. So that'll be more geared towards the application. But I don't know, I don't want to say too much because need 2 months. Any other questions? Yes.
Does your method work for a positively curved hypersurfaces?
Yeah,
So no vanishing principal curvature?
Yeah,
Oh, that's
like
already
the
done.
sphere or paraboloid.
That's already done.
Okay, I see.
But I didn't mention that in the talk. But yes, I should. I tried to say, but I think it wasn't fairly divulged. But yeah, so Bourgain-Demeter in their original paper, proof of L2 decoupling, they provided the full range. So the sharpest range of decoupling for the paraboloid. And then they were able to do the same for these same hypersurfaces using the prominent Ziegler method. And it followed as like a half-page long proof towards the end of that same paper. So yeah, that case was taken care of back 2014 or 2015. But what remains are hypersurfaces that are degenerate in some sense. So some vanish in principal curvature, or maybe even all of them vanish at certain points or all points.
And so your work handles like when all but one principal curvature vanishes.
Right.
So what if, like, I guess a natural follow-up is like if some of them vanish, but some of them don't, could you reduce it? Like, has this been studied?
No, not to my knowledge. I mean, okay. Within the world of decoupling, there's a lot of, there's an increasing level of activity and key players, but I did forget to mention some others. So Li and Yang were able to prove decoupling for smooth surfaces in R3. It's very natural to ask whether it should be decoupling for smooth surfaces.
Smooth, no other condition.
Right, no other conditions, just smooth. And so why they're able to do that is because they provide an honest proof, bare bones proof of decoupling for polynomial surfaces, so graphs of polynomials. And then from the Taylor approximation, they're able to use prominent Ziegler to get decoupling for smooth surfaces. But it's natural to ask whether or not this can be done in 4 dimensions and higher. In their paper, they explain why they didn't immediately try to do that, the key barriers. So that's one thing. And then, yes, you may certainly ask for probably any hypersurface that has some degeneracy, of course, so that you're not repeating what's already been done. As long as it has some kind of curvatures in some manner. It could even be a fractal set, perhaps. Yeah, you would, it could be interesting to figure out decoupling for that.
So does Li and Yang generalize Bourgain-Demeter?
Yes.
Okay.
Yep, they prove a full L2 LP decoupling theorem. So both you get the L2 and the LP cases.
L2 is only for convex.
Exactly.
Only for what?
For convex.
Like ellipses. Otherwise, like Bourgain-Demeter had an LP one with non-convex version. Because there are lines you cannot have. General.
All right, well, it sounds like there's still a lot to be done. So thanks for speaking again.